This video is going to be about the inverse quadratic interpolation method. Here we will cover a simple derivation of the method, the convergence, a numerical example, a comparison between other related methods, and also a brief overview of the advantages and disadvantages of the method. So let's begin with a brief description of the inverse quadratic interpolation method. So an inverse quadratic interpolation is a root-finding method that we can interpret to be a resulting method of the secant method. So let's have a look at the numerical derivation of the inverse quadratic interpolation. So we have these 3 points, x to the n minus 2, xn minus 1, and xn. So these are our initial values. So now to obtain the values of y, we just substitute it into a function f, like so. And we will let g be the inverse of f. So now our initial values will become, for example, xn minus 2 will become g of y to the n minus 2, and so on, as presented here in the last line. So fitting the points into a parabola in y, we can compute the polynomial interpolation with Lagrange basis functions, giving the following result. So to obtain the estimate for the new root x of n plus 1, we will let y equals 0 for the equation that I've shown before. Therefore, we will obtain this new result. And this will be the formula used to obtain values that will tend towards the solution. We use this new point to replace the furthest outer line of the 3 initial points that we had initially, and we keep on repeating this procedure until the error is acceptably small. So now let's look at the convergence behavior. The convergence for the inverse quadratic interpolation method is asymptotically faster than the secant method, but the method can become very poor if the initial values are not picked close enough to the solution. This is one major disadvantage to the inverse quadratic interpolation method. With this concern of stability, if the initial values aren't picked correctly, the inverse quadratic interpolation method is usually used alongside other methods. For example, Brandt's method. So Brandt's method is a root-finding algorithm which combines root bracketing, bisection, and inverse quadratic interpolation. And Brandt claims that this method will always converge as long as the values of the functions are computable within a given region containing a root. So since this method is quite similar to the secant method, the order of convergence can be evaluated similarly to the secant method by letting xn equals s plus epsilon n. So to construct the order of convergence, we let xn equals s plus epsilon n, where s is the solution and epsilon n is the error. So what we want to do is, of course, we want xn, our estimate, to approach our solution, s, when the error approaches 0 as n approaches infinity. Now subbing xn into the new root estimate formula, xn plus 1, and then using Taylor's formula, we will obtain an order of convergence of approximately 1.8392. Now, the workings here are omitted from this presentation because to calculate the order of convergence, it's quite similar to the secant method, which we have already learnt in class. To further demonstrate the convergence behavior, let's look at an example. So for this example, what we have to do is we have to determine the least positive root of this function, f of x, presented here. So firstly, let's have a look at the function visually. So to plot the function, we just let f of x equals 0. Here I've used Maple to plot the graph. Now I'm only focusing on the positive side, so that's for this graph only shows the positive root of the function f of x. So we can see that the positive root lies within an interval from 0 to 2, so therefore we should pick initial values that is within this interval so that we can make sure the inverse quadratic interpolation method will converge and is stable. So let's pick our initial values to be 0, 1, and 2. Next step is to evaluate our y values. So if we just input our initial values back into f of x, we will obtain the y values. And therefore, our initial values are the following. Now, to make sure that we will have convergence, let's plot this, our parabola that we will be fitting, and make sure that it will cross the x-axis. So to do so, we have to plot g of y. So substituting these initial values into our function g of y, like so, and plotting the graph, we can see that g of y will intersect the x-axis. So we can continue on with this method. So the next step is to compute x of n plus 1, so x of 3. And we do so by just substituting our initial values of x and also our values of y that we already computed into our new root estimate shown here, x of n plus 1. We will obtain our new root estimate x3, which it equals approximately 1.255 in this case. And upon substituting this value back into f of x, our function, we will obtain the new approximate value for y as well. And we just keep on repeating this procedure.